Okay, like Eno said, my name is Jeremy Andrus, and I'll be presenting work we've done at Columbia University that we call cells. Okay, mobile devices have become full computers that fit into our pockets. They're so integrated into our daily lives that when our boss comes and says, you get to carry the corporate phone that IT has given you, we say, okay, I'll keep my personal phone, and we now have two devices. I'm sure more than one of us has moonlighted as a mobile application developer, and it's always nice to have an extra phone where you can do testing, debugging, maybe run a different version of the operating system. As a parent, I've often wished for an extra phone where my kids can use all the games and educational things that I've downloaded for them, but can't make random phone calls or purchase things. I have stories you can ask me later. So it would be nice if we could have all of these different facets of our life on a single device. Your business contacts, corporate VPN config could be kept separate and isolated from your personal data. Your kids can't make random phone calls, but can play all the games you've downloaded for them, and you can develop mobile applications in a separate sandbox, all on the same physical device. Now, all these facets need to be kept isolated from each other. Using separate user accounts just won't cut it. For example, the corporate phone has different policies and requirements from your personal phone, and we don't want faulty software in one area affecting other areas. This should sound familiar to a lot of us. We use virtualization on our desktop and server machines to run multiple operating systems on a single virtual machine. Given these desktop and server approaches, there's been some work attempting to apply them to mobile devices to run multiple virtual phones, or VPs, on the same physical phone. There are two basic approaches. The first approach is a bare metal or type 1 hypervisor that's often used in server environments. For example, OKL4 uses this approach on phones. Here, the hypervisor, or VMM, runs directly on the hardware platform and must provide some level of device support in order to manage the resources amongst multiple guests. This is unfortunately difficult to maintain in a fast-paced mobile device industry. I think Samsung might even have released a new device since I started talking. While the bare metal hypervisor can get away with allowing single guest pass-through access to hardware devices, there's really no support for simultaneous access from multiple guests. Now, to alleviate the device support problem of a bare metal hypervisor, we can use a hosted hypervisor. This is popular in desktop products such as VMware Workstation, and in fact, VMware is going to use this in their upcoming mobile virtualization system, MVP. Here, the hypervisor runs on top of a host kernel and leverages the existing device support in that kernel. And in general, the host user space has direct access to devices, but guests have to use an emulation layer. And now, simple things in a guest, such as file access, have to pass through two kernels, the hypervisor, and a piece of emulation code. This adds a huge amount of overhead, and the device performance is too poor to run accelerated graphics in the guest for things such as 3D games or an accelerated UI. In fact, the overhead is so high, we're not aware of any system that can run more than a single guest. Finally, we could give up on virtualization altogether, write a secure, isolated user space SDK to separate environments. Companies like Enterproid or Worklight are pursuing this solution, and now we can have native performance, but users can't download and install apps in the isolated environment or use stock apps they're used to. This solution is also less secure because the isolation occurs completely in user space. There are two key reasons why these existing approaches cannot provide the complete and efficient and transparent mobile virtualization solution that we're looking for. The first reason is device diversity. Desktop and server solutions generally support a smaller set of virtualized devices and then rely on industry-standard interconnects such as PCI or USB to enable device access. However, there is little to no standardization in the way mobile systems are built. Generally, they use a system on a chip with integrated peripherals that all have custom memory-mapped control interfaces that differ from SoC to SoC, vendor to vendor. Additionally, mobile user spaces expect to be able to talk directly with things like the Wi-Fi config, the accelerometer to control your game. You want your location, you want to make phone calls, you want to do 2D and 3D graphics, You want to use your touch screen, AV accelerators. And so when we run multiple virtual phones, each one is going to want simultaneous access to all of those devices. The second key challenge is the usage model. In 30 seconds, I expect to be able to pull my phone out of my pocket, wake it from sleep, check my email, stocks, text messages, maybe play a quick game, put it back to sleep and back in my pocket. In fact, users are so concerned with that fluidity and efficiency of the mobile UI that graphics acceleration has been introduced to increase responsiveness. So again, the device diversity of custom devices and peripherals and lack of standardization, coupled with this new usage model, make mobile virtualization a challenging problem. So we introduced Cells that meets both of these challenges head-on with an innovative solution designed specifically for mobile devices. And we start with a simple observation. Your desktop computer is relatively large, and you generally have several windows open simultaneously and are working on more than one thing at the same time. Your phone, in comparison, is rather small, and in general, you only use one application at a time. In other words, the screen real estate on mobile devices is limited, and users are generally accustomed to using one thing at a time. This observation led us to develop a mobile-centric usage model whose clever simplicity allows us to intelligently and efficiently share resources across all virtual phones. Phrasing this in terms of device resources, only one virtual phone really needs to use a device at any given time. We call that virtual phone the foreground virtual phone. And this is the virtual phone with which users will directly interact. All other virtual phones, or VPs, run simultaneously, but the user doesn't directly interact with them, and we call these the background virtual phones. As an example, only the foreground virtual phone really needs to draw on the screen, and while in a complete virtualization solution, it's important to note that background VPs still need to be convinced they have a screen, but the foreground is the only one that's actually displayed. So we use this foreground-background usage model to build a complete, efficient, and transparent mobile virtualization solution. So first, we have a complete solution. We run multiple isolated virtual phones on a single mobile device, and we have a 100% device support in each VP. That means we can do cool things like assign unique phone numbers to each virtual phone on your device using the same SIM, and we can provide 3D accelerated graphics in each virtual phone. Next, Cells is an efficient virtualization solution. We implemented a prototype using Android and ran benchmarks that revealed less than 2% overhead on a Nexus S device, and this includes 3D accelerated benchmarks. We'll see those in a minute. Not only do we add very little runtime overhead, but Cells also gets out of your way when you want to switch context from one phone to another with an imperceptibly short switch time. Finally, we're a transparent virtualization solution, as each virtual phone can see and use every device on your phone, and you can run unmodified applications from, say, the Android market. You can also switch virtual phones, as I hinted at, just like an app. It's a swipe on the home screen, and you switch. So now that we have an overview of the Cells virtualization solution, let's take a look at how we accomplish this. To make things more concrete, and because we implemented our prototype on Android, I'll use Android and Linux terminology to describe our architecture. So unlike hypervisor-based approaches, Cells uses a single OS kernel, and instead of instantiating multiple guest kernels, we said, why can't we just run multiple instances of Android? And leveraging Linux containers, we do just that. Each VP runs in its own private virtual namespace, and each namespace virtualizes kernel identifiers and resources such that each VP, virtual phone, can run concurrently and use the same resource names, such as PIDs or UIDs, and yet remain isolated from other running VPs. In other words, we virtualize at the operating system interface. Another way to look at this is that each VP is really an isolated collection of processes. Now, because we use a single Linux kernel, we can leverage all of the device drivers and support already available in production Linux kernels, so we don't have to write any of our own driver support code. And thus, we can support the myriad devices available in mobile phones. However, each VP is running simultaneously and is an isolated Android instance that believes it's the only thing running on the kernel. This means that each one will access the same device at the same time, and we need some way to handle that simultaneous access from each isolated virtual phone context. In other words, we need a way to safely, efficiently, and correctly multiplex each access. So here we introduce device namespaces. This is a virtualization framework that allows individual drivers or subsystems to multiplex access to hardware resources, and unlike namespaces that virtualize identifiers such as PIDs or UIDs, device namespaces are designed to be used by devices or subsystems to tag or isolate their driver data. It also leverages our usage model by registering callback functions that indicate when a virtual phone changes state from foreground to background. Each VP uses a unique device namespace when interacting with kernel drivers, and this allows the single host kernel to isolate the access and safely, efficiently multiplex the access to the resource. So in summary, device namespaces coupled with our usage model gives us the complete, efficient, and transparent mobile virtualization solution we were looking for. So now that we have an overview of how Cells works, I want to illustrate how we use the device namespaces and the foreground-background usage model through two key subsystems: graphics and the cellular modem or baseband. So first, I want to show you how we use device namespaces to efficiently virtualize the basic graphics in the Linux frame buffer. Next, we'll see how we accomplish the first complete mobile virtualization solution of hardware-accelerated graphics. And finally, we'll see how Cells is even able to virtualize a proprietary closed hardware system such as the cellular baseband modem. We'll start with graphics. In Android, basic graphics operations are performed through the Linux frame buffer. A frame buffer driver is responsible for a physical resource called screen memory, and this is a region of memory that holds the content which is displayed on the screen. The job of the frame buffer driver is to copy that content onto the screen about 30 times a second. When user space wants to draw something on the screen, it first opens the frame buffer device and then maps the entire region of screen memory into its virtual address space. The process then simply writes content onto the screen, or writes content into the virtual address space, and then calls an ioctl on the frame buffer device to tell it to begin to DMA that content out onto the display. While this is extremely efficient, it's also quite challenging to virtualize. Two basic approaches have been used in current hypervisor solutions, and the first is a single assignment, where the hypervisor simply gives one VP complete control of the frame buffer, leaving others with no access. That's obviously not what we want. So the second way, used by hosted hypervisor, is emulated hardware. In this approach, the host OS generally passes access from a host user space directly to hardware. However, the hypervisor presents an emulated piece of hardware to the guest VPs, which use some virtual state to emulate a device. When the guest wants to draw on the screen, the hypervisor has to copy all the contents from the emulated device into the hardware frame buffer, and while this allows multiplexing, it introduces significant overhead in a system that was designed for maximum efficiency. The Cells solution is device namespaces. We created a new device driver that we call the MUXFB, or multiplexing frame buffer driver. This is a simple device-independent wrapper to the underlying hardware frame buffer, and remembering how a frame buffer works, we allow foreground processes to directly map screen memory into the virtual address space. Background VPs map a region of system memory. So this allows pass-through access from both the foreground and the background VPs. The MUXFB distinguishes the access from the different VPs using the respective device namespace. Now, when a user wants to switch the foreground VP to interact with a different virtual phone, it's really as easy as swiping your finger on the home screen. The device namespace framework uses a callback, and all the MUXFB has to do is swap the virtual addresses mapped to each VP to point to the correct physical location. This means that unlike hosted solutions, background VPs not only run simultaneously, but they get full control of the hardware when switched into the foreground. Now let's see how we extend this basic graphics virtualization to support accelerated graphics. Accelerated graphics is done using the GPU. Unfortunately, the GPU is given a priori knowledge of screen memory and then writes directly into that physical resource. So we have the same basic resource sharing problem we had with a frame buffer. And on top of that, we want all the VPs to be able to use the GPU simultaneously. But we don't want any Angry Birds drawn on top of our work email. Fortunately, the GPU is designed exactly to isolate simultaneous access from different processes. And because we use a single Linux kernel, we can directly leverage this. User space draws using the GPU through the OpenGL library, which isolates processes using graphics contexts. The GPU enforces this context separation using a dedicated MMU that doles out graphics virtual addresses. Remembering back to our architecture discussion, a virtual phone is just an isolated set of processes. So now, all we have to ensure is that processes from background VPs don't draw on the screen at the same time as the foreground VP. This sounds like a problem we just solved, except the GPU doesn't have a standard interface to the OS. However, by adding a small amount of device-aware namespace, or device namespace-aware code to the GPU driver, we can allow background VPs to again use system RAM and pass foreground VP access directly to the screen. By small, I mean approximately 100 lines of code versus 60,000 plus lines of code in the Nexus S GPU driver. That small bit of code also handles the state change callbacks from the device namespace framework, and similarly to the frame buffer solution, it can remap graphics virtual addresses to point to proper physical locations when a user changes a VP state. Okay, that's the Cell solution to graphics virtualization. We'll get some performance numbers in just a minute, but first I want to illustrate how cells can virtualize the proprietary closed system of the radio, a cellular radio, assuming you still use your smartphones as phones. So first, an overview. The cellular baseband is kept as a closely guarded industry secret. Although there are some standard Linux drivers to interact with it, the actual interface is opaque, and in fact, the baseband stack runs on a physically separate processor. This completely rules out any sort of kernel-level virtualization because there's simply no state or interface to virtualize. To further complicate the matter, the baseband chipset manufacturers also provide a user space library responsible for interacting with the hardware. We'll call this the vendor radio interface layer. And as you can guess, this too is proprietary and closed source. In Android, a process called RealD, or the radio interface layer daemon, loads this vendor library and then manages user space access to the cellular radio hardware. So because of this proprietary nature of the baseband stack, others have essentially punted on virtualization. They say in a guest, use VoIP. That's not really the point of having a cell phone, though. Other people say, well, you can use a dual SIM, but unfortunately most phones don't have a dual SIM, and this solution doesn't really scale. Cells, again, begins with a simple observation. Proprietary hardware requires a well-defined interface, and the vendor-provided library provides just such an interface. So now, just as our graphics solution, we leverage our usage model and introduce a user-level variation of device namespaces that we call the device namespace, the user-level namespace proxy. We start by replacing the vendor library in each VP with a cells-aware vendor-independent library that implements the same API. We move the actual vendor library into a root namespace, and we introduce our own daemon process called CellD, which will be responsible for virtualizing that vendor interface. Now when user space accesses the radio through the radio interface layer daemon, the cells-aware library proxies the request through CellD, and CellD then passes access from the foreground directly through to hardware. And as requests from background VPs are sent, CellD can selectively allow some access, such as what's the signal strength, and disallow other access, such as send a text, make a phone call. Note that cell D only proxies control messages, whereas actual data, such as the call audio, is passed directly through to ensure good performance. Cell D also gives us an interception point where we can alter or massage control messages coming from or going to each VP, and this is what allows us to assign unique phone numbers to each virtual phone using the same carrier-provided number tied to your SIM. The details in the paper, feel free to ask me about it later. Now, we've implemented and benchmarked cells on several real devices. Today I'll present Nexus S results. For more results, see our paper, ask me later. Using the latest open source version of Android, we ran up to 5 independent and isolated virtual phones on a single Nexus S device. We're, in fact, not aware of anyone else who was able to run more than 2. And we measured the overhead introduced by our virtualization solution by normalizing performance benchmarks against a manufacturer-provided OS image. We wanted to evaluate all the critical aspects of the system to measure that performance overhead. So we used industry standard benchmarks that we generally downloaded from the Android market, such as LinPack to measure CPU, NeoCore by Qualcomm to measure 3D graphics performance, Quadrant to measure storage I/O, the Sun Spider benchmark to measure your web browsing experience, and we wrote a custom Wi-Fi test to measure network throughput. So, performance numbers. Along the x-axis, we have the benchmarks. The y-axis represents overhead, where 1 is stock performance, and anything above that is additional overhead added by our system. Here you can see we add less than 2% overhead across the board. 2 quick things to note. The benchmark is running in the foreground VP. Network results were somewhat hard to control. However, the variation in any single test, it was actually larger than the variation across all the tests. And from this, we can see that we didn't add any additional overhead. The next interesting thing to note is that we added negligible overhead in 3D measurements even while running 5 virtual phones. So, with these performance numbers, I want to invite my co-author, Christopher Dahl, up to give you a live demo.
Hello, everyone. Do I get this on? Yep. OK, so I'm going to turn on this phone. And the first thing you'll notice is that it looks and feels completely like a standard Android phone. You can unlock it, swipe between home screens, show the application launcher. That's it. Now, you're looking at my virtual phone. It has this cool rocket as the background. And Jeremy has another virtual phone running. I can switch to it by simply swiping across the home screen. Unlock his virtual phone. It looks completely like a standard Android phone. Swipe back to my own phone. I'm going to launch this game called Angry Birds. 1 or 2 of you may have already heard about this game. It's about shooting pigs with Angry Birds. And you'll notice that, I'm on World 4, Level 4. Go ahead here and try to actually do something. And not too good at it. But luckily for me, Jeremy is actually even worse. You'll notice that he's only on World 1. And let me see if I can help him out here a little bit. You'll notice that it's running completely as if you're running on a native phone. There's no noticeable performance overhead, and it's running really smooth. Actually, we can change between the 2 sessions of Angry Birds in flight, and kind of play against ourselves or like a race against time, I guess. So if I switch back to my own virtual phone and press the home button, it works like a normal phone. I go to my home screen. And I can run NeoCore here. We have the background virtual phone configured to allow audio, so you can hear Angry Birds at the same time, still running. And I'm going to show you this benchmark that actually shows live rendering of 3D graphics. It heavily utilizes both the CPU and the GPU. And I'm going to show you how that runs while Angry Birds is running in the background. You can see we can still switch, or we should be able to. I mean, it's a little bit resource constrained. Yeah, so this is an early prototype. Thanks. And you know, if any of you want to try it out, we'll have each one of them one in our pockets. So come and find us, and you can play with it.
So quick wrap up. We presented efficient, complete, transparent smartphone virtualization. And to do this, we created novel kernel and user-level device namespace mechanisms that isolate virtual phone instances while efficiently multiplexing access to all system devices. Our solution is designed from the ground up for mobile devices, using our foreground-background usage model to cleverly and intelligently share device resources. And again, we implemented a prototype on Android and measured less than 2% overhead on a Nexus S device. So that's, for more info, you can see our website, and we've actually commercially licensed this to CellRox, so you can check out their website as well. So with that, I can take some questions.
So I love this work. I'm Mary Baker at HP Labs. I think this is wonderful. Congratulations. I really enjoyed this. I did have a question, though, about if I understood one of your assumptions at the beginning, that in general, people only have one thing that's really doing anything on the screen at a time on their cell phones. And I'm wondering if that's a little bit of a chicken versus the egg kind of a question, that there have been many phone systems where that's really all you could do was one thing at a time. I find myself doing multiple things at a time, and we can play with my phone afterwards if this is of interest, and there can be multiple things, cards, doing stuff on the screen. So I'm wondering if people were more used to that, if that would be less of a possible assumption to make. And also, with tablets and things where you might want to be able to run essentially the same system, if that assumption is as viable there.
Yes, so you say you actually run multiple things at the same time. Actually, I'd be curious to see how you use your phone.
Yeah, we can play with that, sure.
Because, again, that screen is small enough that you have some status icons on the top, but generally there's one application.
No.
But, okay.
So that's my point. Is I wonder if that, going into the future, if that's an assumption that will really be able to hold true. You do have to have other ways of compensating for the small display space, absolutely, although that's slightly less true also with tablets. So
yes.
I wonder if that's an assumption that will really hold firm.
So in fact, we have thought a little bit about that and how to extend this into a tablet. And we've thought about interesting ways of maybe splitting the screen, splitting the device resource between a couple of different virtual phones or something like that. This is an area that we're looking into.
Okay. I'd love to talk with you about that if that's possible.
Definitely.
Thank you.
Hi, Craig Souls from HP Labs. So how do you deal with notifications that come in, right? So like if one application, like if one virtual phone has the entire frame buffer, and the other phone like gets a text message and wants to like pop something up on your screen to tell you while you're playing Angry Birds that, oh, you got an important text message. How do you deal with that, or is this something like future work type thing?
So yes, how to deal with notifications between. This is a little bit of future work. We didn't implement things, but the basic idea is that we have a daemon process running that can proxy these things between virtual phones. And so depending on how you might configure your device, maybe you don't want text message notifications showing up in your work phone from your home phone. So you would have to configure this, but you can use a daemon process to proxy those messages back and forth.
Cool, thanks.
Yu Feichen from Fudan University. A simple question. So why don't you just let Android to have multiple user accounts and then enable user to quickly switch between different user accounts and enforce some access control to separate the user data or something like anything else? Yes,
that's a valid question, and the answer is really that to have the complete isolation, especially for a corporate environment where generally you have specific policies and things that IT requires, multiple user accounts just isn't the way to go. You can't enforce the security and isolation that those environments need.
Last question.
Hi, Joel Nider from Qualcomm Israel. First, I'd like to say it looks like a really nice phone with a very powerful processor. Good choice. But my question is actually about multiplexing the modem. You mentioned that you could actually have different phone numbers for each of the personalities. How can you multiplex that if you have incoming calls from different numbers at the same time?
Yes. Quickly to address your first comment, we've ran this on a Nexus 1 and a Nexus S and actually an NVIDIA Tegra tablet.
That's
So,
okay.
The multiple phone number multiplexing is done using a VoIP service where the phone numbers are registered, the DIDs are registered through the VoIP service, and then this VoIP service calls the single carrier number. And on the phone, cell D intercepts the incoming call, looks at the incoming caller ID, and what the VoIP service does is append a digit to the caller ID. And we look at that digit, and this is associated with a virtual phone, and we pass it through to individual virtual phones. So multiple incoming calls, you can use things like call waiting. You can leverage call waiting. And on top of that, I mean, you only have maybe 2 lines or N lines on your GSM, so that's kind of a limitation there.
Okay, thanks.
Okay, thank you. We're out of time here.